Okay, this is a quick tutorial on uh, reaction rates with more than one reactant. So you'll see that this reaction is going to depend on two reactants, and the method of initial rates involves you run different trials. So we have 4 trials, and you run the trials varying the concentrations of each reactant, and then you measure the rate of disappearance of that reactant by measuring the concentration over time. You want to do this, carry out this experiment so that you keep one of them constant and then vary the other reactant, and then you'll see that the rate here was dependent on just this one. So it's a way to isolate one of the reactants by keeping the other one constant. So you'll see we do something similar where we choose 2 trials, and then you take ratios of the 2 trials in order to cancel out the variable k, which is the rate constant. And it's important if you have more than one to keep it constant, keep one of them constant while changing the other. And you do one at a time. So we're gonna have to do two. This problem we're gonna have to do 2 steps. So the first one, I'll try to use the black ink. So we're going to choose trial 1 and 2, because in that one, this one is the same and this one's varied. And then in the second part of this problem, we're going to choose 2 trials where this one's constant and this one's changing. So it looks like, inspecting that, it looks like this one's 1 here and 1 here. Meanwhile, fluorine F2 changes here and here. So on the second part of this problem, we're going to be using trial 1 and trial 3 and taking a ratio of those. Okay, so let's start. Go to the next slide, and I think I have the data table, yeah, on the next slide. So here's the first part of the problem, is trial 2 divided by 1, and I always try to use the bigger number over the smaller number. So you could go rate 1 over rate 2 for your ratio, but that would result in a fraction. That would result in 1 over 2. So I'm just going to flip those and do rate 2 over rate 1. And then you write the rate law. You write that out, so there'll be NO2, and I'll call the order with respect to NO2, I'll call that X, and the order with respect to F2, I'm going to call that Y. Okay, and then we just plug in numbers here. So we're going to plug in, actually, let me write it down here. So we're going to plug in, now I'm just going to like drop those out. So this will be 2.00 divided by 1.00 equals k. And then it's important to plug these in accurately. So we're doing 2 over 1. So this will be 2.00 to the x over 1.00 to the y. Okay. And then from trial 1, we get these numbers, 1.00 to the x, and this number goes here, 1.00 to the y. Alright, so you'll see that because F2 was kept constant, you'll see that this whole term here cancels out, including the y, which is the whole reason you do this, to reduce this to just x, and you'll also notice k cancels. So you'll see that x equals 1 here. You're going to get 2 equals 2 to the x, therefore x must equal 1. So this reaction is first order with respect to relative to NO2, the concentration of NO2. Okay, and then keeping the ink the same color as before, I'm going to do trial 3 over 1. So I'm going to use these numbers here. Okay, so I'm going to do, instead of writing rate, I'm going to just put R. So R, I made a mistake, R3 over R1. So that would be 2 over 1, 2.00 over 1.00. You're probably seeing that you could probably do this in your head. And it's not always clean like this though, so that's 1. So I'm writing this number right here, 0x and 2.00 for y. This number 1.00 x, and then this number goes here, 1.00 to the y. So you see that all of that cancels, and y would equal 1. So it's also first order relative to f2, and the overall order of the reaction is the addition of the two exponents. So it would be 1 plus 1. So the overall order of this reaction is second order, considered second order. We're not quite done. I think this problem asks to solve for, it says determine the order, the overall order. Usually these problems are going to ask you to solve for k, so I'm going to go ahead and do that. You could pick any one of these trials, and then since you know what x and y are, you could plug those in and then solve for k, because you'll have all the other numbers. So solving for k, we could pick, why don't we just pick reaction 3. So we'll say rate 3 equals k into, and I'm putting it in terms of the rate law. We know what x is, and we know what y is. So let's plug in some numbers from trial 3. And make sure you write the units. This is important for the correct units for k. So 2.00 times 10 to the negative 4 molarity times inverse seconds equals k. So using trial 3 and the values for NO2 and F2 for trial 3, NO2 is 1.00. Keep the molarity there, times concentration of F2, 2.00 molar to the first power. So when you solve for k, it's going to be 2.00 times 10 to the negative 4th over 2.00 molar squared. Okay, because from this you're going to get 2.00 m times m, so it's going to be m squared. And it's really important to make sure you write the units here. On the AP exams, this is a very common question. When you get kinetics problems, they always tend to ask what are the units for k if it's a second order reaction or a first order, or even a zero order. So when you solve here, you'll see that one of these will cancel and then that will cancel. So you're going to have inverse molarity times inverse seconds, and those are the units for second order, the units for k. So k would be 1.00 times 10 to the negative 4th inverse molarity times inverse seconds. And sometimes you might see it actually written like this. You might see it written like this: liters over mole times seconds, which is the same exact thing. These two, this and this. So writing the whole thing, this is the rate law. This is the rate law. So it would be k, which we know what k is now, so we'll write it like this. Times NO2 to the first power, the initial amount, times the initial amount of F2, also to the first power. And then that is the rate law. And again, the rate laws show proportionality constant and the concentrations of the reactants at a constant temperature. And it also allows us to determine the order, and then these numbers, the order has to do with how many molecules are colliding during the rate determining step. So these are a couple of these topics are things that we are going to cover towards the end of the week. All right, that's it.